Hi, we're Group 8. We're doing a 3D portable printer project for our senior design project. And yeah, thank you for coming to our presentation.
So my name is Zachary Yor. I'm the computer engineer of the group.
My name is Michael Doyen. I'm one of the electrical engineers.
My name is Joseph Tuckerman. I'm another electrical engineer.
And I'm Jack Wells. I'm the third electrical engineer. So our design goal for this project was to create a portable 3D printer that's accessible and convenient to an even larger range of 3D printer enthusiasts. Whether you're a college student or a professional, everyone's busy, and we want to have a printer that is portable and can be used in a multitude of different environments. We want it to be meet the industry standard of other commercially available printers while providing all the advantages that we tout about our project. So, of course, we mentioned portability. We wanted to be able to operate untethered, meaning not plugged in, off of a battery and renewables. We wanted to be precise and accurate, as well as fast, more at the same level or more so than other commercially available printers. Want a long print time, of course, with it being battery powered. That is our main constraint in this project. So we want to make sure that we, to the best of our ability, address that issue and squeeze as much power, as much print time as we can out of our project. Also needs to be easy to use. Ease of use is really important for a wide range of consumers. So we want to make sure that even people who are just getting into 3D printing are able to enjoy our printer and have a good time using it. As mentioned before, innovation. This project is not something that's been done a whole lot. It'd be very easy to take a standard printer and modify it to run on a battery, which already is a problem within itself. But as you'll see later, we made some design decisions that make our printer even more different from others that you may have seen. Accessibility, we want it to be approachable for everyone, professionals and novices, as mentioned before, and reliable. We want to make sure that our printer is going to operate as intended at all times. And then we're not just designing something for the senior design showcase, we're designing something that can go out and be used by anyone. Technological advancement, as mentioned before, this isn't an easy project. We were very aware of that jumping into it. We want to make sure that we do a good job with it. User empowerment, again, ease of use, very important for these kinds of things. We don't just have engineers using these kinds of printers. This is something that'd be very useful for someone who's an art major, for example, as well, or making other kinds of models. And consistent performance, again, this is a project that we're spending a lot of time on to make sure that it's going to be reliable and meet the standards of other commercially available 3D printers. Here are specifications for all the different main components of our project, whether it be the stepper motor, battery pack, or 3D printer control board. We'll go a little bit more into these parts in the next few slides.
Okay, so here's our overall hardware block diagram. We have two power sources. We have our solar panel and our wall outlet charger for our 24-volt battery. We have the 24-volt battery outputting to the two of our regulators, one 24-5 and one regular 24, and then a voltage divider. And a voltage divider goes to our ADC, which will help the Raspberry Pi out. And here's some of our peripherals, and the CDR Pico is our printer control head.
So here's our 3D printer control boards. So first off, we have our Big Tree SQR Pico, and next our team considered the Duet 3 Mini 5 Plus. Now, both have pros and cons to them, as we will see in the next slide. Here's just a better detailed illustration. So as you can see, the Pico is much cheaper, which is something, we're trying to make this thing as accessible as possible. Along with this, with the MCU clock frequency, the SQR Pico did outperform the Mini, even though it does have the higher price range. As you can see with the next slide, we did decide to go with the SQR Pico not only because of its price and fast processing speed, but maybe even more importantly, we went with it just because of its compact design. It fits within 85 by 56 millimeters. Also, it has something very special amongst the control boards, is that it needs a Raspberry Pi to function because of the MCU on it, and this makes the board much faster than traditional boards.
So here's our two battery packs we considered. One's the Talent Cell. Here's a couple of reasons why we would have chose that, and here's the QZF battery as well. This one is intended for e-bikes, and here's a couple of reasons why. Well, I'll show you on next slide how. So the Talon Cell is a little bit cheaper than the QZF overall. You have a little bit more options with the Talon Cell as well, with 3 voltage profiles, higher capacitance, smaller dimensions, lower weight, and they're both lithium ion. And we'll show you on the next slide what we went with. So we went with the Talent Cell for a variety of reasons: smaller size, smaller weight, higher battery capacitance, great charge hours, and overall lithium ion higher charge efficiency. And yeah, that's pretty much it.
So this is our current PCB schematic. To the very left, you'll see a circuit for our battery. Pretty much it's just the circuit that connects the solar panel to the battery. Towards the center, you'll see the Raspberry Pi footprint along with its inputs and outputs. And next to that, you'll see the footprint for the ADC, as well as the voltage divider circuit that feeds into the ADC. And then at the top, you'll see the 24 volt to 5 volt voltage regulator that is responsible for powering the Raspberry Pi and peripherals. So for our PCB design selection, we chose the 24 volt to 5 volt voltage regulator, which has a constant 2 amp output, which is just enough to power the Raspberry Pi and all the peripherals connected to it. The voltage divider is going to be responsible for checking for fluctuations in the battery's overall voltage level over time. And we'll be using an ADC module to convert analog measurement of voltage divider into either a 1 or 0 for Python script.
So for the structural design, particularly the gantry, we need a design that would maximize print speed without hurting our print quality. And one way to do this is to keep the center of the mass in the printer low, which reduces jitter if you have something heavy on the on or near the print head or the lateral linear guide rail. You tend to get a lot of movement if the printer tries to move a lot faster. So we had a couple different options. Still the typo here, but we've got a traditional Cartesian gantry, which requires 3 stepper motors, and then a non-traditional Cartesian gantry with a cross design here, or a traditional looking Cartesian gantry, but the belts highlighted in green and yellow you can see are orientated much differently, so that you have a very different control scheme. But more importantly, you can only need the 2 stepper motors to drive the 2D motion of the gantry. So between these options, we ended up going with the non-traditional Cartesian gantry, which mainly because the cross non-Cartesian gantry required a special cable that was a little bit out of our price range. But this design still achieves a lot of the same things, like keeping the center of mass low, only using 2 stepper motors, so we don't need to power 3 stepper motors all the time to have it running. It also needs a more nuanced control scheme, which is one of the drawbacks of it, which could cause some issues or additional challenges down the line in terms of implementing the G code. As shown in the next slide here, the control. So if you move both stepper motors in one direction, you get it to move left or right. If they move in opposite directions, it'll go up and down. And then lastly, if you move it just one stepper motor, you'll get diagonal motion. So that could cause a little bit of challenges down the road, but it's something that we knew going into this, and we're prepared to address. So additional structural challenges, we've got the extruder and print bed. One issue with these is when you heat them, it's going to cause a lot of draw on the battery to be constantly heated. So we're looking to insulate them in a way that will make them consume a lot less power and stay at the desired temperature for much longer without needing to pump more power into it. And for the Z-axis, we need to make sure that it'll be lightweight enough to not necessitate the Z-axis stepper motor to need to hold or use any additional power to hold the print bed, since we are printing upside down, to hold the print bed at a certain level. Additionally, it needs to be precise enough to adjust to 3D printer layer height, which is usually around 0.5 millimeter to 1 millimeter. So precision will be something to keep in consideration there.
So here are some of our hardware design challenges. For our PCB for the CDR Pico, we need to design a regulator circuit capable of efficiently meeting the high power demands of the Pico, since it needs 24 volts and 10 amps for all the peripherals attached to it. Some of our plans are to make the Droke buck converter circuit and take that circuit and make a custom built regulator circuit in the future. Also, we would need a better power delivery for the Raspberry Pi. We need to design a regulator circuit to meet the power demands of the Pi and the peripherals, which is about 5 volts and 2 amps with everything connected to the Pi.
So as you can see here, this is our team's software block diagram. Essentially, our block diagram starts when the printer is turned on. So first off, we'll have a Python script located on the Raspberry Pi. And what this will do is it will first, using an ADC, send that voltage level to two different screens. Now, the first one being an onboard touchscreen, it will use a software called Clipper screen. And then also it will send it to a local host network called the mainsail. And now it will also determine if the voltage is above 20 volts. If it's above 20 volts, it'll still be able to print, and it'll just keep repeating until the print's finished. Now, if not, this is where it gets a little interesting. It'll stop the print first off, and then it will display to the user, please plug in the battery. It needs to be charged, as well as save the progress of the print. Now, some of these softwares we'll be using to develop our project, I'm sure you're familiar with a lot of these. GitHub, Raspberry Pi, Vim, PyCharm, Mainsail, Clipper, and Adafruit. On the next slide, you'll see some that you may not be too familiar with is Mainsail and Clipper. Now, Mainsail, as described before, is a web interface designed with Clipper, which is our firmware we'll have on our 3D printer control board. Here is what the Mainsail interface would look like on your mobile device, laptop, phone. So you would type in 3dpp.local on your device, and this screen will pop up displaying very important information about our printer, and also our voltage level and various other information we want to send. And Clipper is the firmware of our choice that is flashed on the Raspberry Pi as well as the control board. Clipper is one of the fastest firmwares control boards can use, so that's why we determined this. It's also open source, so we're able to change almost everything about it. So here's just a more in-depth software implementation on each subsystem. So like I said, we'll be using an ADC to determine the voltage level, and it's an Adafruit ADC. So it comes with built-in packages we can import in for the Python code. The Clipper API, which will be in the Python code, which will allow us to send commands to Mainsail. The touchscreen, now the touchscreen is a little different. It uses a firmware called Clipper Screen, which again is open source, but we will need to go in and change a little bit of front end and back end changes to the code. And again, Mainsail, which is the the web application will be sending the voltage level to. Now, the biggest design challenge we're going to come up with our project is the saving the progress of the print in case of a battery failure or the battery just dying. So the problem with this is we need to be able to access a file, save it to a file where it just doesn't go away once the battery is dead. And also printers generally calibrate prior to printing. So to save where we left off, we won't be able to do that, but we believe that is a design choice we'll be able to overcome.
So this is just a list of standards that our project's going to be following. Some of these standards include standards for rechargeable lithium-ion batteries and safety for them, guidelines for how to write Python code, guidelines for the stages of software testing, guidelines for just general printed board design, and then standards for the analog to digital converters. So this is our bill of materials. Our current estimated total is $888.37. As we continue developing our project, we have plans to reduce costs as much as possible to make this as accessible as possible.
So for our team, like mentioned prior, I'm the computer engineer of the group. So I'm responsible for all microcontrollers and software applications. So far, I believe that on my end, 70% of the software is completed. So what we've done here is we've flashed both the microcontroller, which in our case is the Raspberry Pi, as well as the 3D printer controller with Clipper, our firmware of choice. And as well as we've written a Python code that reads the voltage level from the Adafruit ADC. And from that, we just have if statements that say, if it's this value, do this. If it's not, do that. So that's about where we are at this point. So in the future, we will need to incorporate our mainsail, printing that value on the local host network, as well as changing that Clipper screen code, which is that open source code for the touchscreen, so that we can display it there.
I'm Michael Doyen. I would say my progress is about 50%. We still need to work a bit on the PCB design, add a bit more peripherals and user accessibilities like off and on switches and LEDs, things along that line. I also need to work more on the power consumption side, try to make that as efficient as possible as well. I'm also working with Zach on the ADC software, doing the Python scripts. And I also am working a bit more on the printer peripherals as well.
So my name is Joseph Tuckerman, and I believe I'm also around 50% done with the printed circuit board design. What I need to finish, I need to finish the buck boost converter circuit, which is responsible for powering the SKR Pico side of the power delivery system. And then I'm also going to be looking into ways to better insulate the hot end to conserve as much power as possible, or rather reduce power consumption as much as possible.
I'm Jack, estimating I'm around 65% done. The structural team lead and the gantry, which we have a working prototype for, was a big part of the structural design of the project, but we still have a good amount to do in terms of the build plate, and then as well as the print head, which could have its own set of difficulties. But more importantly, I need to integrate the print bed and the print bed and extruder, and meet with Michael to make sure that we're saving as much power as possible, putting any proper insulation so that we're using as little heat as possible to get those parts to the desired temperature. So a lot of that right now is looking for both parts that are already commercially available, as well as deciding how much of that we'll have to modify or even like design our own parts in those scenarios.
So overall, we would say that we're roughly 60% complete with our project. And you know, we just completed the toughest part, which was just designing the printer overall. And next up on our list, we'd like to create a software solution for saving the progress of the print in case of the battery dying. We'd also like to optimize the printer once the initial prototype is complete to get the most out of our battery. And we'd also like to work on incorporating more features into the PCB design. You know, again, like the on-off switch, LED indicators, things like that. And then we'd also like to design a foldable printer system to make the printer as compact as possible for our users.
All right, that was our presentation. Thank you very much for listening. If you have any questions, hopefully you wrote them down. We'd be more than happy to answer them. Thank you.